The next statistical topics we're going to cover in this lecture are central tendency, skewness, and everyone's favorite, degrees of freedom. So before I talk about skewness, I need to talk about central tendency. So for any given sample of data, we can calculate its central tendency. We can do it in one of three ways. We can calculate the mean, median, or mode. And I'm sure this is a refresher for most of you, but here's an example. Let's say I counted 10 plants, the number of insects on 10 different plants. I got numbers from 1 to 7. I arranged that in descending order from smallest to largest. I can calculate the mean, median, and mode pretty easily. Now, by definition, in a normal distribution, the mean, median, and mode are the exact same number. They're all equal to each other. When they're not, then we have a skewed distribution. So by definition, if we have a skewed distribution, it would not be a normal distribution. So let me just give an example of what I mean by that, and then we'll talk about implications. So on the left, you can see a standard normal distribution where the mean, median, and mode are all the same. And on the right, you can see what we call a right skewed distribution, or a positive skewed distribution, where we have some extreme values to the right, much greater than the mean. That's pulling the mean away from the mode and the median. So we have some extreme values here that's skewing the data to a positive skew or a right skew. We can also have negative skews or left skews, where we have much small values that are pulling the mean away from the median mode towards the left instead of the right. But in any case, when we have skewness, there's some implications. So first off, when you have a skewed probability distribution, it's not a normal probability distribution because by definition, the mean, median, mode are not the same like they would be with a normal curve. Okay, now what does that mean? So, we have to accept, some degree of skewness in most real-world data sets. Most real-world data is never perfectly normally distributed, and some degree of skewness is not a big deal. We can still proceed as normal with our statistical tests and with our summary statistics. We can also look at outliers, if these extreme values are really real or not, and we can exclude them if we have justification to do so. Now, if we have very high degrees of skewness, very, very skewed data, and I would call the graphs you're looking here borderline. I might not do anything about them. They don't seem to be too skewed. But if you have very skewed distributions, then there are statistical techniques you can use to account for that kind of skewness. I finally want to talk about degrees of freedom because it's kind of a confusing concept, but it's very important when interpreting test statistics. You're going to have to calculate degrees of freedom in, for example, your term projects and basically for the statistical tests that you're going to do. So what is degrees of freedom? It's the number of values that contribute to a given test statistic or value that is free to vary. And generally, the way we interpret it is the greater the number of degrees of freedom that go into a test statistic, the more confident we can be in that result, and the less likely it is to be overfitted, which is something I'll explain in just a moment. Here's a quick example. We have a sample of 7 numbers, and the average of those 7 numbers is equal to 8.3. The degrees of freedom for this average, or the mean, is equal to 7 as well, because 7 data points went into calculating the average, and each of those data points was free to vary. Right? They could have been whatever they want. But this is not true for the sample standard deviation and variance. The degrees of freedom is not going to be equal to 7. It's going to be equal to 6. Now, why is that? Remember that we know that the deviations of each sample, when we add them up, must add up to 0. And here you can see what I mean by that. Here for all of the 7 values in the sample, we have their deviation from the average. And this is pretty straightforward. So if we know what the mean value is, and we know what the deviations of the first 6 values are, right? If we know that, for example, the first 6 values add up to a deviation of negative 11.7. Then we know that the 7th value, the deviation of that 7th value has to be equal to 11.7 because the sum of them have to equal to 0. So if the deviations add up to 0, you can add up the first 6 numbers or n-1 numbers, and then that last data point, you don't even have to measure it. It's not free to vary. It has to be a number such that you're adding up those deviations. They add up to 0. And so our degrees of freedom here is not 7, it's actually 6. because if we know the mean and the and the deviations of all the other data points, then we by definition know the value and the deviation of that final data point. It's not free to vary. So that's degrees of freedom. Another way to think about this is when we're doing regressions, how the slopes of regressions are, if the slopes of regressions are free to vary. So if we look on the left, we have a regression of x over y, and that slope is equal to 3.2, but it's not allowed to vary. There's no variation here, and we have basically an overfitted model because our r squared is equal to 1. It's basically saying that our model predicts 100% of the variation in the data, and we only have 2 data points. And so the slope is actually not free to vary. Whereas if we have 3 data points, all of a sudden, we do have some freedom to vary. We actually have 1 degrees of freedom for error. So when we calculate degrees of freedom for these regression slopes, we always subtract 2. We don't subtract 1. Now, we can calculate degrees of freedom. We're going to do that later in the course. But generally, it's equal to the total number of data points that went into the statistic minus all the number of calculated parameters used in intermediate steps. This becomes very important in experimental design, how we assign degrees of freedom. So basically, this is what you need to understand from the lecture. Just understand these concepts.